In this video, we will abstract the notion of the dot product, which worked so well previously to encode or describe the geometry of R2 and R3. We will abstract this notion to an arbitrary vector space, and we'll call such an abstraction an inner product space. So let's recall the theorem that we saw in the previous video, the theorem that if V is R2 or R3, that the dot product satisfied these four important properties. So what we'll do now is take these four important properties and change them into a definition for a more general thing which we'll call an inner product. So first we'll take this word theorem and erase it and replace it with the word definition, and then we want to consider not just R2 or R3 but an arbitrary vector space. And then we need to name the new thing that we're going to define, and we're going to call it an inner product. So like the dot product, it will be a map on the Cartesian product of V with itself. So it will take ordered pairs of vectors and send them to a real number. But we'll need some new notation. We're not going to use dot anymore. We'll use the following notation. We'll denote the inner product by parentheses, and we'll see how that notation looks in practice. And then we want to state the properties that the inner product should satisfy. So we say the inner product is a map such that for all u, v, and w, u, v, w, and v, and scalar c and r, we have the following properties hold, but I need to make one important change. I've changed notation from dot to parentheses, so I'll go through and make that change. And so now the properties look like this. So for example, I would read A as the inner product of u with itself is non-negative, and the inner product of u with itself is 0 if and only if u is a 0 vector. I would read part B as the inner product of u and v is the same as the inner product of v and u. That is, the inner product is commutative, and so on and so forth. So now this is a definition rather than a theorem. So the next thing we should certainly do is look at some examples of inner products other than the ones that we've already seen in R2 and R3. So our first is not a radical departure. It is a natural generalization of the dot product on R2 and R3. Let V be n-dimensional real space, and for two vectors u and v, each with n components, and here each written as an n by 1 column vector, we define the inner product of u and v to simply be the matrix product u transpose v. Of course, just as was true for the spaces R2 and R3, this will be equal to the product u1 v1 plus u2 v2 plus all the way to un vn. And you can verify, the important thing is, and you can verify that this inner product satisfies all of the properties of the definition given previously. But again, this isn't such a radical departure. This shouldn't be so surprising. This is a very natural generalization of the dot product on R2 and R3, and in fact, we should still call this the dot product on Rn. But there are some more unusual examples we'll look at now. So our next example is this. Let V equal R2 again, and let U and V be two vectors in R2. We're going to define an inner product. This one will not be the standard inner product or dot product that we saw previously. Rather, we'll define the inner product of U and V to be the following expression: U1 V1 minus U2 V1 minus U1 V2 plus 3 U2 V2. Now, it seems that we're picking the signs and orders of these terms almost arbitrarily. In a sense, I suppose we are. And the whole point of this example right now is to convince you that there are inner products other than the standard dot product. Now let's look at an example where the vector space is a little more exotic than Rn. For this example, let V be the vector space of all continuous real-valued functions defined on the interval from 0 to 1. So this vector space is not so similar to Rn. In fact, this vector space isn't even finite dimensional. So this V is not isomorphic to Rn for any n. You can't write the elements of V as column vectors with a finite number of column entries. So how will we define the inner product? Well, we'll define an inner product like this. Let's take two vectors in V, and in this case, vectors are functions. So let's take two functions, f and g in V, and define their inner product as follows. Let the inner product of f and g be the definite integral of the product f times g on the interval from 0 to 1. Let me remark that you certainly get a real number. This is certainly a way of taking two vectors and creating a real number by sticking them in here. But to assert that this is an inner product requires that we go through and verify that the four properties we listed above for inner product hold in this case. And so that requires checking. We have to check, for example, that the inner product of any vector with itself is non-negative and all of the other properties. I'm not going to go through the entire verification right here. I will verify one fact just so we can see how it goes. And I'll make a comment about another one of those properties that needs to be verified. So first of all, let's just begin and verify the first property, that the inner product of any vector with itself should be non-negative. Here's that property written down. Let f be a vector. Is the inner product of f with itself greater than or equal to 0? Well, we have a definition now. The inner product of f with itself is the following. This definition is the inner product of f with itself is the definite integral of f times f, or f squared, on the interval from 0 to 1. So here's what we know about f squared. Of course, if we're squaring f, then we're always getting a non-negative number. And then since the function is always non-negative, it's a standard result, which one typically sees at the beginning of a course on integral calculus. Standard result that if f squared is non-negative, then the integral of f squared is non-negative as well. You can intuitively justify this to yourself, for example, by recalling that if f squared is non-negative, then this integral measures the area under the curve from 0 to 1, and that should be a non-negative number. So we could be a bit more rigorous about it, but the verification certainly holds. The property holds that inner product of f with itself is non-negative. The only other comment I wanted to make is about the second part of property A. Remember, A says something else. It says that the inner product of f with itself should be equal to 0 if and only if f is the 0 vector. Here, of course, the 0 vector is the 0 function. So this is a statement that goes in two directions. One direction is the following. It is, if the inner product of f with itself is 0, can we conclude that f must be the 0 vector? Well, if the inner product of f with itself is 0, then what do we know by definition here? We know that the definite integral from 0 to 1 of f of t squared is 0. And from here, we would like to conclude that f is equal to the 0 function. Well, this is true, and your textbook makes pretty short work of it. In the text, it just says, well, if the definite integral of f squared is 0, then f must be equal to 0. But this statement deceptively requires a significant amount of proof. In fact, at this point, it must suffice for us to simply say that this follows by a theorem in advanced calculus. The verification of the remaining properties, B, C, and D, pretty much goes off without a hitch using standard properties of integrals. and you can verify those or check the text to see how those are verified. They're all true. We can conclude that this particular product is an inner product on the vector space V of all real valued continuous functions on the unit interval.